Hello and welcome to the Unit 4, Section 1 video on cubic function, key features, and transformations. So we're going to start off by talking about what a cubic function is, and we're going to do that by talking about the cubic parent function. So a cubic function is a polynomial where the highest power of any variable is 3. So we've done linear functions and we've done quadratic functions. Those have a highest power of 1 and 2 respectively. Now we're moving on to a function that has a power of 3 in it. Now the graph of a cubic function is a curve that is either always increasing or decreasing, and therefore it has no absolute maximum or minimum. But it can have relative maxes or mins. So let's talk about a parent function. So we've done this already for absolute value functions and quadratic functions. Now we're going to do this with cubic functions, and the parent cubic function is x cubed. Okay, so we're going to take our table here, and let's start in the middle. 0 cubed is easy. 0 cubed is just 0, so that's our output. 1 cubed is 1. 2 cubed is 8, because 2 times 2 times 2 is 8. And then 3 cubed is 27, because 3 times 3 times 3 is 27. Now when we go to the negative values, negative 1 times negative 1 is positive 1, times another negative 1 gives us a negative 1. Okay, so every time you cube a negative number, you're going to get a negative answer out of it because you're multiplying by 3 times. So you end up with a positive times a positive, or I should say a negative times a negative, which gives you a positive, and then a positive times a negative, which brings you back to a negative. So our values here are negative 1, negative 8, and negative 27. So let's go ahead and graph the parent function. Now, we're not going to be able to graph the negative 27 and positive 27 because our graph is not that big, but we can do the other 8 points. So let's start in the middle with 0, 0. That's right at the origin, and that's easy to plot. Then we go over 1 and up 1 for 1, 1. And then we have 2, 8, which is over 2 and up 8. 1, 2, 3, 4, 5, 6, 7, 8. And we can similarly go back to negative 1 and down negative 1. And then negative 2, negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then from here, we can draw our curve. And it looks something like this. You can probably draw it better than I can. That's a little bit of a shaky drawing, but you can kind of get the idea. It's always increasing. We go from concave down to concave up. All right, let's identify some of the key features. And you're going to have your own graph here to kind of go by. All right, so let's take a look at some of the key features here and see what we have. So the function shape is that it's always increasing. Okay, the x-intercept is at the origin, and so is the y-intercept. The domain for this is negative infinity to positive infinity, and that's always going to be the domain for your cubic function. And that's going to also be the case for a range. You're going to have negative infinity to positive infinity. Now the rate of change, it's constantly changing. So our rate of change from the origin to 1, 1 is 1, but then from 1 to 2, 8, or 1, 1 to 2, 8, our rate of change is 7. And then from 2, 8 to 3, 27, well, that rate of change is 19. And so our rate of change is continuing on in that fashion. All right, our positive interval is from 0 to infinity. Our negative interval is from negative infinity to 0. And again, you'll have your graph to kind of look at that, but these are our key features for the parent function. Well, it's always increasing. We already described that as our function shape. So our increasing intervals from negative infinity to positive infinity. Since it's always increasing, then there's no decreasing interval. And then for end behavior, as x approaches infinity, f of x also approaches infinity. And then as x approaches negative infinity, f of x also approaches negative infinity. And that's because it's always increasing. Okay, if it was always decreasing, then your f of x would flip. And you'd have negative infinity as x approaches infinity and positive infinity as x approaches negative infinity. All right, well now let's talk about some cubic transformations. The nice thing is if you know absolute value transformations and you know quadratic transformations, this part should be fairly easy for you, okay? Because the transformations behave pretty much like those other two function types. The only difference is we don't have a vertex in a cubic function. So instead of hk giving us the vertex, it's actually going to give us what we call the inflection point. And what the inflection point is, it's the point at which we go from concave up to concave down or concave down to concave up. So the inflection point will behave very much like the vertex because that's going to give us our starting point when we do some graphing. So let's talk about the rules. And again, this is going to be very similar to what you already know. So there's not really much new to learn here. A horizontal translation happens, which to the right, when you have h being positive. Now remember, h will not look positive because it follows a minus sign in the form, okay? You have a horizontal translation to the left when h is negative. Okay, and again, it's not going to look negative because it follows a minus. So let's show a couple examples of what it looks like. You would have f of x equals x minus 2 cubed. And then when h is negative, you would have x minus negative 2 cubed, which would look like x plus 2 cubed. Now, vertical translations up and down behave very much like you would expect it to. If k is positive, then you're going up. If k is negative, then you're going down. So, it would look like this. F of x equals x to the third plus 4. F of x equals x to the third minus 4. Okay, so the k value is what's not in the parentheses. It's usually right on the end. A reflection across the x-axis occurs when a is negative. So it would look like this. F of x equals negative x to the third. A reflection across y occurs when x is negative. And so the negative sign would have to be in the parentheses as part of what's being squared. Okay, you have negative x to the third, or I should say what's being cubed in this case. All right, you have a vertical stretch when a is greater than 1, and you have a vertical compression when a is some number between 0 and 1. So you would have, for example, a stretch would look like this. F of x equals 3x to the third. So you would have a vertical stretch by a factor of 3. And in a compression, this would be a vertical compression by a factor of 1/3. So that's how this all works. Now let's do some examples. And again, this should all be somewhat familiar. So in example A here, we have a vertical stretch by a factor of 3, and we are being translated left by 2. Okay? In B, you have a reflection across the x-axis. And you have a translation down 4 units. All right, for C, you have a translation to the right by 6, and you have a translation up by 2. And then in D, we have lots of things going on. We have a reflection across the x-axis. We have a vertical compression. By a factor of 1/3. We are translated left 1 unit, and we are translated down 5 units. Okay, so again, if you're familiar with absolute value transformations and quadratic transformations, then these should be no problem for you. All right, let's move on to example 2, where we are graphing each function, and then we're going to identify a couple of key features. So let's start off by graphing, okay? We need to know 2 things to be able to graph this. We need to know what our h and k are, and we need to know what our a is. So h and k come from here and here. So our h is -2, because remember, this is actually x minus -2, which makes it a plus. So h is -2, and our k is -3. And then our a is 1, because there's no number out in front of this parentheses. So that tells us it's a standard graph. So we start from -2, -3, which is here. This is going to be our inflection point. Since we're standard, we're not stretched or compressed. So we are able to graph this by going over 1, up 1, because 1 cubed is 1. Over 2 and up 2 cubed, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to do the same on the other side. We've got over back 1, down 1, and then back 2, down 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then from here we can sketch our curve through the points. Now, where is our y-intercept? Well, our y-intercept is at that point that we found when we were sketching our points. So that would be at 0, 5. And for our end behavior, as x approaches infinity, f of x is also going to infinity. As x approaches negative infinity, f of x also goes to negative infinity. For b, we need to find our h, k, and a again. So h here is positive 1. Our k is positive 5. And our a this time is negative 1, indicated by that negative sign out front. So let's go ahead and do our h and k. That's over 1 and up 5. This is standard, but it is decreasing. So we're going to go over 1 and down 1, over 2 and down 8. 1, 2, 3, 4, 5, 6, 7, 8. And we don't have quite enough to do 27. Not enough space. We can go over 1, back 1, and up 1, and we don't have enough space to do 8, so we'll go ahead and draw our curve the best we can. Now, domain is going to be negative infinity to positive infinity, and range is also negative infinity to positive infinity. These are the easiest features to find on a cubic. All right, let's move on to C. So we're going to plot this one. Our h is 3, our k is -4, and our a is 1/2. So we go over 3, down 4, and we plot our point. And then, since we are compressed by a factor of 1/2, we would go over 1 and up 1/2. Instead of going over 2 and up 8, we'd go up 4. And instead of going over 3 and up 27, we go up 13.5. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.5. Because 13.5 is half of 27. And then we can go back 1 and down 1/2. We can go back 2 and down 4. 1, 2, 3, 4. And that's all the points we can do. So from here, we can sketch our graph. And again, my graph's going to look a little rough. You can probably make yours look better. The important point here for our key features is where our x-intercept is, which is at x equals 5. Because our positive intervals are going to be from 5 to infinity, and our negative intervals are going to be negative infinity to 5. All right, one more example. This one, we have an h of, and actually I'm going to write this over on the side here. We have an h of -2, because this is the same as x minus -2. K is going to be 5, and our a is 2, indicating that we are stretched, and that the function will be increasing. So, from here, let's see if we can graph this function. So we go over back 2 and down, or I should say up 5, our h and k. And we are stretched by 2. So we go over 1, and instead of going up 1, we go up 2. And it's going back down 2. And going back 2, instead of going down 8, we're going to go down 16. So let's see if we have enough space to do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have just enough space to do that. And so now we can draw the sketch of our curve. And it's going to look something like that. So let's do our rate of change, okay? So we want the rate of change from -4 to -1. We're going to need 2 points to do this, x1, y1, x2, y2. Our -4 and -1 give us our 2 x values. So we need our y values to go with it. Where our y that goes with -4 is -11. And the y that goes with our -1 is 7. So from here, we'll use our formula for average rate of change, which is change in y over change in x. So you got y squared minus y1, or I should say y2 minus y1, over x2 minus x1. Well, y2 is -1. y1, or I should say, our y2 is 7. Our y1 is -11. Our x2 is -1. And our x1 is -4. So 7 minus -11 is 7 plus 11, which gives us 18. 1 minus -4, which is -1 plus 4, that gives us 3. So we end up with an average rate of change of 6. All right, the last thing we want to do to wrap this thing up is we want to write an equation for the graph of the given functions. Well, just like before, what did we pick out of the equation to graph? We picked out our h, k, and a. Well, to write the equation from the graph, we're going to need the same information, h, k, and a. So our hk is our coordinate for our inflection point. And for this one, it would be 3, 4. And A is going to be our compression or stretch. Well, if we go over 1, up 1, that tells us that our A value is 1 because we're increasing and the first point is standard. So from here, we can write our equation. And the equation for this function would be f of x equals, we don't have to write the 1, so we can start with x minus 3 cubed plus 4. And that would be your equation. Over here for b, we have our hk being, well, we're going back to -6 and we're not going up or down, so that's 0. So -6, 0. Our A is, well, let's check. We're decreasing, so we know it's going to be negative. And if we go over 1, down 1, we hit the graph, so that's going to be -1. So f of x equals -x plus 6 cubed. All right, 2 more examples. We got in C, our h and k would be the inflection point. So we got -4, -5. And our A, well, we know we're going to be positive because we're increasing. If we go over 1, we have to go up 2 to hit the graph, so where you have a stretch of 2. So our equation will be f of x equals 2x plus 4 cubed minus 5. And then our last example. Again, we start with our inflection point, hk. So we go over none and up 3. So we have 0, 3. Our a, well, we're decreasing, so we know our a is going to be negative. And we go over 1, down, it looks like a half, but we're not entirely sure. So let's check 2. If we go over 2, we go down 4 to hit the graph. And 4 is half of 8, so our compression value is indeed 1/2. And so our equation for this becomes f of x equals -1/2. And we don't have to use the parentheses because we don't have an h to put in with it. So we can just do x to the third plus 3. And that's the equation for that one. So that wraps up section 1. Coming up in the next section, we're going to talk about some new forms of factoring for these higher order polynomials and use that to be able to solve for what our x values are in higher order polynomials.